So now that we know what the idea behind local linearization is and the definition, let's apply it to a specific example here. Use local linearization to estimate the square root of 67. So the problem doesn't even tell us what the function f of x is or what a is, the value where we sort of know what's going on. It's up to us to figure that out. So if you didn't know any calculus at all, what would you say? Square root of 67 is probably about what? Probably about 8, right? Because you know a perfect square near 67 is 64. So the idea is we choose the function to be square root of x, and we have to choose a place where we know what's going on. So that's why we choose 64, because we know the square root of 64 is 8. Going back to the previous example, we know how much snow there is on the ground at this time. So if we're looking at the picture, we know that at x equals 64, the y value is 8. We want to follow this tangent line over to 67 and figure out what the y value is going to be up there on the tangent line, because we don't happen to know the square root of 67, right? Now, there are other places we could have chosen for a. You could have chosen a to be, 49. That's a perfect square, 36. But this is the one that's closest to 67. So that's the one that's most local. So that's the one that will give us the best approximation. So that's our function f of x. Now, what else do we need to know about this tangent line? We need to know the slope. But luckily, we know calculus. So we know how to find slopes of lines, right? Slopes of curves. This is x to the 1/2, so the derivative is 1/2 x to the negative 1/2, which might look a little nicer if we wrote it as 1 over 2 square roots of x. And that's going to let us figure out what the slope is at 64. So f prime of 64 is 1 over 2 square roots of 64, which is 1/16. So we'll write out the answer with a formula in a minute, but as was the case with the week 4 problems, if you're able to do this with the calculus and then just sort of think about how this graph works and write out the answer from there, that's great, as long as you show enough work to show us how you figured out the derivative. So let's figure out what the answer is going to be. Here we are at a y value of 8 and a slope of 1/16. So when we go over 1 unit on our tangent line, we should go up 1/16 of a unit. How many units do we want to go over? We would like to go over 3 units to get to 67. So every time we go over 1 unit, we're going to go up 1/16. If we go over 3 units, we should go up 3/16. Therefore, our estimate up here should be 8 plus 3/16. That's the answer we're going to get when we use the formula. If you don't want to use the formula, if you just want to understand it this way, that is great. So let's try to do it with the formula. So we've got f of x is approximately f of a, which was 64, plus f prime of a, which was still 64, times x minus a, which is still 64. So f of 64, that's how much snow there was at the time we started measuring, 8 inches. F prime of 64, how fast was it snowing? Pretty slowly, 1/16 of an inch per hour, x minus 64. So this is the equation of this tangent line. If you were to multiply it out, if you wanted to get it in y equals mx plus b form, that would be fine. But this is the equation of that tangent line. And we want to know the value of the tangent line where? At 67. So therefore, f of 67 will be approximately 8 plus 1/16 times 67 minus 64. I hope that's looking familiar. That's 8 plus 3/16. And if we wanted to write it all in one nice fraction, that's 131 over 16. So that would be our estimate for the square root of 67. If you were to put this into your calculator, you could see how close it is. But just from the graph, can we tell whether this estimate is too big or too small? This is our estimated value right here. And the exact value is down here, right on the curve. So from that, we can see that our estimate is too big. And why is it that the estimate is too big? Is it because we went to the right instead of to the left? No. In fact, even if we'd gone to the left, our estimate would still have been higher than the actual curve, right? What was it about this function f of x that made our estimate an overestimate instead of an underestimate. It's that the curve itself is what? Concave down. That's what matters. Anywhere you draw a tangent line on a concave down curve, if you go back to our day where we studied concavity in the first place, any tangent line on a concave down curve will always lie above the curve. So whether we had gone to the left or the right here, we would still have gotten an overestimate. Two more things. One, you might wonder, why do we do this? We have calculators. Well, you want to understand, in some sense, one thing that you want to understand is how your calculator does these sorts of things. When you ask your calculator what the square root of 67 is. It is some more complicated version of this, but it's essentially the same sort of idea, that it uses a simpler function to approximate a complicated function like square root of x, or sine of x, or e to the x, or natural log of x, or arctangent of x, or any of those hard functions. Another question would be, why couldn't we have gotten even closer to 67? Like, why couldn't we have used our a to be 66? What would have happened if we tried that? Well, then, when we tried to figure out what f of a was, it would be the square root of 66. Do you know the square root of 66? I don't know the square root of 66. If you had some magic way of finding out the square root of 66, well, then just go ahead and apply your magic way and find out the square root of 67 exactly, and then you don't need to do any estimating. This is, we actually do know the value at 64 is 8, and that's why we choose our a to be 64. So we now have an applet. We actually have two applets for you. We have one applet that just explores this, and then we have another applet that explores, suppose that you were doing a different tangent line approximation at 49, how the approximations would compare. You want to compare what happens when you do it at 49 and what happens when you do it at 64 to see which one will give you the better approximation for values between 49 and 64. Just something for you to explore and play around with.